Okay, testing again. Testing, yeah. Okay, so today is lecture 8 of the course. That's right in the middle. And we're going to have 15 lectures, so this is the central lecture. And to remind you that in 2 weeks' time from now, or 2 weeks from yesterday, so on the 22nd of April, there's the quiz in the exercise class, and the quiz will count potentially to 10% of your mark, 10% plus mark. You'll get more information about this by email over the next week or so. And today's lecture is going to contain the last material that will be examinable, if you like, in the quiz, but quizable. I mean, we're not thinking of it as an exam. So anyway, that will be material that might be asked in the quiz. So today, last lecture, contributing to quiz material. Are there any questions about this quiz?
Will there only be one?
There will only be one quiz. And if you can't make that exercise class, then I'm very sorry. Then you can still get full marks on the course. It's just you have to get them on the exam, on the written exam. Your one opportunity to get marks on the practical side of the course from something other than the written exam. Okay, so as I said, it's the central lecture of the course, number-wise, lecture 8 out of 15, and it's also very central topic-wise, in that today we're going to return to the topic of cardinal arithmetic, and it's going to be the main lecture in which we do the cardinal arithmetic of infinite quantities. Cardinal arithmetic and the thing is, in previous forays into cardinal arithmetic on this course, we've had one hand tied behind our back, so to speak, because we haven't had the axiom of choice. Last week we covered the axiom of choice. We're going to now assume the axiom of choice for today, and that's going to mean that we can then address cardinal arithmetic in the level of generality people normally deal with it. So it's cardinal arithmetic in the present, which we didn't have before, of choice. So henceforth, today, we're not going to always have choice for the rest of the course. It'd be nice to do some things without choice when we can. But henceforth, for today, we're going to assume the axiom of choice. Assume. We have it with us, but nonetheless, I'm going to flag when we need it, so when we use it. One of the main points of it is it makes cardinal arithmetic manageable. And that's because lots of subtle distinctions we've been having to keep in mind previously on the course all get easily. You don't need to worry about these subtle distinctions anymore because the axiom of choice just makes things very straightforward. So the axiom of choice, as we saw last week, is equivalent to the well-ordering principle. Every set can be well-ordered. So what does this help us with as regards to cardinality? So we have, from the point of view of cardinality, we have that every set can be well-ordered. So every infinite set has a cardinality that is an aleph, because those were the cardinalities of initial ordinals, and every well-ordered set is an aleph. We saw that 2 lectures ago. So, so every infinite cardinality is an aleph. In other words, if x is infinite, then cardinality of x is aleph alpha, that is the cardinality of an initial ordinal omega alpha, for of course a unique initial ordinal, for of course a unique ordinal alpha. Or the alpha itself need not be an initial ordinal, but omega sub alpha, whose cardinality is aleph alpha, is initial for a unique alpha. So we have a numbering system indexed by the ordinals for infinite cardinalities. So also, we proved 2 weeks ago that every aleph is its own square. And so every infinite set is its own square. Well, let's phrase that about cardinalities. Every infinite cardinality is its own square. By the way, the statement that every infinite cardinality is an aleph, in other words, every infinite set is equivalent to an aleph, that's easily equivalent to saying every set is well orderable. So that is, for this property, is equivalent, not just a consequence of the axiom of choice, but it's equivalent to the axiom of choice. Also, the statement that every infinite cardinality is its own square is equivalent to the axiom of choice. So I seem to remember finding, I mean, at least I think that's the case. I seem to remember finding this online about 3 years ago, but it's not trivial. Let's put an exclamation mark after that. And I'll try to find the link again, and I'll put a link on the course homepage. You don't need to know the proof of that, but it's an interesting fact that this in itself implies the axiom of choice. And another simplification, we get to the notion of cardinality. We have the less than equals relation on cardinality that we already had in the second lecture of the course, corresponding to one set being embeddable by an injection in another. And if we have the axiom of choice, then that less than equals relation is a total order, a linear order. So cardinalities are linearly ordered. Well, how do we see that? Well, clear for finite cardinalities, infinite cardinalities are alephs. So if we've got a pair of infinite cardinalities, one is aleph alpha and one is aleph beta, well, the ordinals are totally ordered or linearly ordered, same thing. So either alpha is less than equal to beta or beta is less than equal to alpha, and so aleph alpha is correspondingly less than equal to beta, or the other way around. And again, this is equivalent. This statement, that cardinalities are linearly ordered, is again equivalent to the axiom of choice. That's a little exercise for you, but you basically use what's it called? That the function that finds the smallest order, the Hartog's function. You use for half of that. And second, and not secondly, the fourth point is that we have this subtle distinction between a cardinality being strictly below another cardinality in the order and a cardinality being very strictly below another. And if you have the axiom of choice, that distinction disappears. Strictly below is the same as being very strictly below. So we don't need to worry about this very strictly below concept. So the relations strictly below, namely one set embeds in the other, but there's no bijection between them, and very strictly below, one set embeds in the other and there's no surjection, the first and the second, are identical, they're the same relation. I have no idea whether this statement is a choice or not, but it's certainly a consequence. Yeah. And again, it's an easy exercise to verify this from the accident choice. So I'll leave that as an exercise. Okay. So once we know that every infinite cardinality is an aleph, well, also 2 lectures ago, we proved that if we have a coproduct of 2 alephs, then you again get to have a coproduct of sum of 2 sets. If they're both well orderable, you again get a well orderable set. And the cardinality, if they're infinite, is just the maximum of the 2 cardinalities. And also with the product of 2 infinite sets, we saw that if the cardinalities of each of the infinite sets are alephs, then the product itself is again its cardinality is an aleph, and again the cardinality is the maximum of the 2 cardinalities. And we saw that 2 weeks ago for alephs, but now every cardinality is an aleph. So just for every infinite set, for all infinite sets, so this is another consequence, for all infinite sets, x and y, we have the sum of the cardinalities is simply the maximum of the two cardinalities of x and y, and that's the same as the cardinality, the product. So sums and products should be clear enough. Product. Sums and products have a very simple rule for calculating the cardinality. And of course, yeah, I mean, this is really, you have aleph alpha plus aleph beta. You could write this like this. You have aleph alpha plus aleph beta. Then that's the same as aleph max of alpha beta. And that's the same as aleph alpha times aleph beta. Okay. So we have an extremely simple arithmetic of sums and products. The arithmetic of exponentiation is going to be much more complicated, and we'll get onto that later on today. But beforehand, on the topic of sums and products, well, we have a very simple and in a sense quite boring arithmetic of, we've got binary sum and binary product, so this is basically finite sums and products. But what about infinite sums and products? Do they make sense? And indeed they do. So let's start off by looking at what happens to cardinal arithmetic for infinite sums. And to motivate that, we look at standard set theoretical constructions that we've already used, namely the sum and the product of not just 2 sets, but of a family of sets. So suppose I'll write it like this, but we're thinking of it. So S here is the class of all sets. And I we're thinking of as an index set. And so we've got a family of sets indexed by the set I. Then we define the sum over the index set of the xi's to be We've already met this in earlier lectures, so I'll just remind you, we were encoding this as pairs, where the first component gives us an index, and the second component gives us an element of the set that's indexed by the index. So here we require I, the index, little I belongs to the index set, and X belongs to the X set at that index, the appropriate set from the family at that index. And product of the family of sets indexed by I, the index set I, xi, is, we were using this last week, at one point, when we showed that the axiom of choice was equivalent to Cartesian product of non-empty sets is non-empty. This is exactly a Cartesian product of the family of sets. And remember that we can view this as the set of all functions from the index set into the union of all the sets in the family. It enjoys the property that for all index elements I, f of I belongs to the set xi. Those such functions are sometimes called choice functions. And because for each index I, we're choosing an element, a function is choosing an element out of the set xi. And we've also sometimes referred to such things, sometimes use the notation like this. Such a choice function, and also view it as we call this a family of elements from the family of sets, capital Xi. So this is the notation for a choice function. And it's also called a family of elements, also known as family of elements. Okay, so the idea, you have such a thing, you view it as a function from the index set to the elements, but it's natural to use this family notation because we have a family of capital Xi sets. The family of elements is like a fact, as it says, it's an indexed family that gives us a number. And it's kind of standard math going between two things. So we have the sum and the product of a family of sets. And when we did binary sum and product in week 2, I emphasized that these operations are functorial in a certain sense, and also these, I call them dependent products, are also functorial in various senses. I'm only going to illustrate one aspect there. So if we have a family, we have two families of sets, there's the indexed by the same index set, capital I. We have the capital X sets and the capital Y set. And if we have a family of functions between them, between the corresponding index sets, then we can derive functions so we can derive a function from the sum of the x's, the x sets, to the sum of the y sets. And how does this work? Well, it's very easy. We take an element in the sum here. So that's given by an index, little I, and an element, little x, belonging to the set x sub I. And we map it to, well, can somebody tell me where we map it, what we map it to over here? So I, what's that?
X.
Sorry?
The I.
Yeah, so we need to, so the index stays the same, but we need to take our little x in x sub I to something in y sub I. So the function f of I will do that for us. So we apply the I indexed function in our family of functions and apply that to x. It's the right place. Okay, so that's maybe I'll yeah, let's do it downstairs. So that takes us from the sum sets, but we also have a mapping on the product set. So here we're going to map an f, a choice function selecting elements from the x sub i's. We want to map that to a choice function on the y sub i's. So that's a choice function. So we're going to need to map some element I, and some element little I we need to map to an element of y sub I. Well, we can get an element of x sub I by applying f to I. Oh, but maybe I'll call this G, yes.
Oh, it was fine because the.
But yeah, but it's because it doesn't have an index, but still it'd be easier to call it G. So we go to, so we can get, if we apply G to I, we get an element of x sub I, and then we apply f sub I to that, and we get an element of y sub I. Okay. And these operations are again functorial in that if the xi's and the yi's are identical, so it's the same family, and you have the identity functions everywhere, then you get the identity functions here, and also they preserve composition in the natural way. So these operations preserve identity composition. So i.e. they are functorial. The reason for flagging these is I want to now state a tiny result. And we're going to basically going to put these operations to the similar use to the use we put analogous functoriality properties of sums of the binary sum binary product in lecture 2. And remember that there, what we wanted was that the sum and binary sum and the binary product preserve cardinality equality. So if you have sets x and y, then x plus y, and they're the same cardinalities as respectively as x prime and y prime, then x plus y will have the same cardinality as x prime plus y prime. We would like to get something similar for these indexed sums and products, so for infinite sums and products. And indeed, we are going to have that. So suppose, so do I call this a theorem or a proposition in the notes? Okay, proposition. Suppose xi, I and I, and there's an I index family of sets called X, and another I-index family of sets called Y sets. Enjoy the property that for all index elements, cardinality of xi is less than or equal to the cardinality of yi, then the cardinality of the sum of the xi's is less than or equal to cardinality of the sum of the yi's. And cardinality of product is less than or equal to this. The sum is less than or equal to the cardinality of the product. Cardinality of the product of the x's is less than or equal to the cardinality of the product of the y's. Okay. So it's not surprising but I'd like you to pay attention while I'm proving this, because there is a slightly tricky thing that goes. It doesn't look tricky. So by the assumption, which is bar, so each xi has cardinality less than or equal to yi. So we have an injective function from xi to y. So for I star, for every I, index little I, there is the injection, meaning an injective function, the injection f sub I from xi to y, right? So now applying this functoriality properties, applying the functorial actions, meaning these two things on the board here, the functorial action for term and the functorial action for product, applying the functorial actions to the family formed from these injective functions from xi to yi, we get functions let me call this function defining it to be this, so I should probably put it down here. So I'm going to call this function itself the sum of the f's, and I'll call this function here product of the f's. That's just giving it a name, so we can refer to. So to get functions, we get the sum function of the fi's from sum of the x's to some y's, and similarly get a product function from the product of the x's to product of the y's. And from the definitions here, it's just very easy to check that these are injective. We could also apply the kind of considerations we were applying in lecture 2 about basically functors almost always preserve injectivity apart from one case when there's an empty set involved, and then we deal with that specially. But it is easily checked. It is easily checked that both the and this is true, it's easily checked. So there's no trick here. You can verify it for yourselves. it directly follows from definitions. This should be the product are injected. And so we're done. Okay, so this proof is completely fine, but there's some issue that needs to be flagged about it. Can anyone see what it is? So what I want to flag is that the proof, this property itself, the proof uses the axiom of choice. So can somebody see where that
Is it by first line, by every injection function to choose that injection?
right? So this line is actually true without choice because we're not choosing one. But when we write this, well, I should have made that an index. So here, when we make it an index family, here we mean there is a function from the index set to that is returning for each index little I the corresponding s of I. And there we are using choice to get this family. So to internalize the existence of a function at every index element as an actual family, that requires choice.
And the first line, we're not actually choosing anything.
We're not actually choosing anything, although the notation makes it look as if we are.
And in the second one, we're actually.
In the second one, we're necessarily choosing because we're writing it as a family, which means a function from the index set to the. Yeah, it means an element of I in I. The function space x, y, I to the x. Yeah, deal. Okay. But anyway, so that is. So here. Here we use the axiom of choice, and so that's flagged that this proposition uses the axiom of choice. I always find this a bit disturbing, but I mean, it's just true that it needs the axiom of choice. But this looks really innocuous because you've got the natural operations of sums and products, and you merely want to say that they respect. Well, we're not even saying respect cardinality classes here. We're saying respect the order relation of cardinalities. But as a corollary of this, so let's write the corollary in green. Corollary is that exactly the same assumptions. If the families have the same cardinality, then we get an equality here and an equality here. That just follows immediately using the Cantor-Schroeder-Bernstein theorem to go from the two inequalities in each step. One inequality in one direction and the inequality in the other direction give us an equality. So we have that sums, index sums, and index product preserve cardinality. Respect cardinality. And therefore, it makes sense to talk about makes sense to talk about if Okay. Kappa I is a family of cardinals Now, what do I mean by this? So we know that every infinite set has cardinality in Aleph, and finite sets, we know their cardinalities are natural numbers. So for cardinals, we can simply take initial ordinals as representatives of cardinals. Remember, every natural number is also an initial ordinal. The cardinals, just from now on, I mean, depends how I use it, because sometimes I use cardinality to be the concept of being in the same equivalence class of sets with respect to bijection. But if I refer to a cardinal as an object, I mean the initial ordinal. I will sometimes write that initial ordinal as omega sub alpha if it's an infinite initial ordinal. And I shall sometimes write it as aleph sub alpha. And I'll write it as aleph sub alpha if I want to emphasize that we're talking about a cardinality, and omega sub alpha if I want to emphasize its quality as an ordinal. But it's kind of not always easy to know which symbol is best to use. So, you know, one kind of make some judgments on this. But anyway, the cardinals from now is the class. Cardinals is the class of initial ordinals. And if kappa sub I is an index family of cardinals, now it makes sense to talk about the cardinal we can simply talk about the sum of the cardinals and the product of the cardinals, indexed by I. So we tend to use, so just like we use alpha, beta, and gamma for ordinals, lambda for initial ordinals, sorry, lambda for limit ordinals, we tend to use kappa for cardinalities as a sort of general symbol. This is a small Greek letter kappa. And this cardinality is just defined to be the cardinality of the indexed sum of for each cardinal kappa I, you take the down set of it, where this is the same notation as before. We're interpreting kappa I as an initial ordinal, and this is the set of all ordinals strictly less than kappa I. So just to emphasize, we're still using ordinal here. So a set of ordinals less than kappa I. And the product of cardinals is again the cardinality of product set. And this makes sense as a concept. I mean, actually, you can make these definitions anyway, but they're not really very robust notions unless you know that index sums and index products respect cardinality quantities and the cardinality order. And because they do, this gives us a robust notion of an infinite sum of cardinalities and an infinite product of cardinalities. Okay. So then, the rest of the lecture is going to be, we've understood finite sums and finite products of cardinalities, as I reminded you at the beginning of the lecture. The rest of the lecture is going to be really about understanding infinite sums and infinite products of cardinalities, and also cardinal exponentiation. But we'll see cardinal exponentiation is a special case of an infinite product. So that's somehow understanding infinite sums and infinite products is kind of as much as we hope to do with cardinals, and it's going to be a very problematic thing to do. But infinite sums turn out to behave very well. So for infinite sums, I'll first do a special case. So now I'm actually going to use lambda for a cardinality, just in order to have enough symbols. So suppose lambda and kappa are cardinalities. Then what we could do is we could consider the sum over all ordinals less than lambda. So we're summing over the cardinality of lambda many things. We make it a sum, but we make it a constant sum. So for every index, so there are lambda many alphas, and for every index alpha, we just take kappa. So we're doing kappa plus kappa plus kappa, times finitely lambda many times. Intuitively. But it's just true in general that if we take an index sum of sets, and for every index element, we always put the same set in, well, that set has a very simple description. So it's the set of pairs where little I belongs to I, and the second component is in X. So what's a simpler description of this set?
I times X.
Sorry? I times X. So this is just the product set, I times X, because we're not actually putting any dependency into that component. So unsurprisingly, this is the way I've defined the index sum. This is actually equality. You don't even need a bijection. Yeah. So unsurprisingly, this is just the product of the two cardinals. Yeah, because of this. Okay, so that's the special case. That's going to be helpful in the general case. So the general case is going to be a theorem. Let's put it on the other board. So suppose lambda is an infinite cardinal. And we're going to use lambda as an index set. And for every lambda, we have a cardinal, kappa, sorry, for every, so lambda is going to index things by over the we view lambda as the set of ordinals strictly smaller than it, which is the set that has the canonical set that has cardinality lambda. And for every such smaller element in the index, which is an element of the index set, we have the cardinal kappa sub alpha. And we require all the kappa sub alpha to be non-zero, but they don't need to be infinite, they can be finite. So our non-zero cardinals. So then we can calculate the sum over all the kappas, and it's simply lambda times the supremum over the indexing elements of the kappas. So this product formula generalizes, but on the right-hand side, you take the supremum of all the supremum of all the cardinals. That's your sum. And notice that here we're taking a supremum of cardinals. So that's a supremum of initial orders need to get cardinal back. Okay, good. Well, that's the statement of the theorem. It's time for a break. And we'll break until 3:15. But I encourage you to think about whether you can prove this for yourselves during the break, because it's like a relatively nice little proof that, yeah. Cardinal multiplication. And we're not multiplying the ordinals, we're multiplying the cardinals. So you take the product set and you look at its cardinality. We know that is a well-orderable set because so you take the unique initial ordinal and gives it its cardinality, and that's what we take. Yeah, okay. And because it's cardinal multiplication, it's commutative. Yeah, good. Other questions? Right, so we'll break until 3:15. Okay, did anyone manage to prove this over the break? I assume the card game had started before because you managed to successfully prove it. But anyway, it is good to have a break. So let's prove it. Before doing so, so we're assuming lambda is infinite. Then there's this assumption that the kappa alpha are non-zero. That is necessary. So it's a nice exercise to find a counterexample in the case that you have an infinite lambda, but you don't require the kappa alphas to be non-zero. So you allow some zero entries there. But anyway, we'll deal with the assumptions as they are. So we assume lambda is infinite and kappa alpha is the kappa alphas are non-zero. So what we're going to do is we'll just use notation kappa for the supremum of the kappa alphas. So the supremum over all the alphas less than lambda, those are the alphas we're indexing over of all the kappa alpha, which, as I mentioned, is because it's a supremum of initial ordinals is an initial ordinal, so it is indeed a cardinal. And so what we want to prove is this equality. So we need to prove that the sum of the kappa alphas is equal to lambda times kappa. We simply introduce the notation kappa for this part. Okay. So as is usual, to prove a cardinal equality, the easy way to do it is to prove two inequalities. So we'll first prove that the left-hand side is less than equal to the right-hand side. But since kappa alpha is less than equal to kappa, because kappa is the supremum of all the kappa alphas, we have that the sum over the alphas of the kappa alpha, well, we proved the monotonicity of sum with respect to the cardinal ordering, the ordering of cardinalities at the start. That was this proof that used the axiom of choice. So this, we can replace the kappa alpha everywhere with something higher, namely kappa. So this is less than equal to the sum of alpha less than lambda of the kappas. But we already saw that this equals lambda times kappa, so by previous proposition. And that's one direction. In the other direction, we have that so for the other direction, we have obviously that kappa alpha is smaller than the sum over all alphas less than lambda of kappa alpha, because this is just one. If we view this as like a co-product of all these sets, then this is just one component of it. There's an easy injection here to here. So, because kappa is the supremum of the kappa alphas, every kappa alpha is less than equal to this, so the supremum is also less than equal to it. The kappa is less than equal to the sum of the alphas of kappa alpha, because kappa is a supremum. And also, lambda, well, the cardinality lambda, so this is a set with one element for each ordinal less than lambda. So that's the same thing as summing over the alpha less than lambda, just a one element set, right? We're just taking lambda many disjoint copies of the one element set, and so that's the same as cardinality. Or we also get this by the proposition we had before, because this, the cardinality of this is lambda times 1, anything times 1, so is lambda. And once again, now we're going to use the fact that the kappa alphas are non-zero. So then 1 is less than equal to every kappa alpha. So again, by the monotonicity of sums, we get that this is less than equal to the sum alpha less than lambda of kappa alpha. But then, if kappa and lambda are both less than equal to the sum of this, that means that lambda times kappa by monotonicity of product is less than equal to the product of this, because lambda is less than equal to this sum times the same thing, because kappa is also less than equal to this sum. And we wanted to get that lambda times kappa was less than equal to this sum once. So what's going to give us that? What's that? that we mentioned right at the beginning of the lecture. The consequence of the excellent choice. We want this. So what fact is this? Yeah, every cardinality is its own square. So this cardinality is its own square. Because alpha is its own square. Okay, so and this formula basically tells us everything we need to know about cardinal sums. So, for example, a corollary, and one can get lots of corollaries out of this, but I'll just do the one that's in the notes. So this is often useful. I mean, in as much as cardinal arithmetic is useful, it's not the most useful. So set theory is a very useful subject, has a lot of applications in mathematics. Cardinal arithmetic itself, I'm not sure, is very useful, but it helps us orient ourselves within set theory, and we understand sets better if we understand the sizes of infinite sets. Anyway, in this course, I'm a bit focusing on cardinal arithmetic from time to time, but doing many things outside of cardinal arithmetic. Anyway, if one needs to do something with the cardinal arithmetic of sums, then I'll say this fact is basically tells us everything, but one's quite often in a situation where you can simplify. So you're quite often in a situation that your index set is relatively small with respect to the cardinals that you're indexing. So, for example, lambda is not strictly greater than the supremum of the kappa alphas. Sorry, this is supposed to be alpha less than lambda of the kappa alphas. Then what do we get in this case? We simply get that the sum over the alphas of the kappa sub alphas is simply the supremum of the kappa alphas. So why does this fall out from here? Well, we know it's lambda times the supremum, but lambda is less than equals to this. So it's just the result that we had at the beginning, that the product of two infinite cardinalities, is the maximum. And they're infinite because lambda is an infinite cardinal. Okay. Yeah, and once again, also, sorry, this should have been the kappa alpha here. Well, again, not every cardinal is its own square, but every infinite cardinal is its own square. And again, we use the fact that it's infinite. Yeah. Okay, so that's, as I say, this basically tells us everything we need to know about sums. So let's go on to products. And products are going to be a bit trickier. And why don't I just start with, so the first thing we're going to do is a really nice result that relates sums and products. But this is, it's a nice transition from sums to products, because you see kind of, unsurprisingly, products are bigger than sums. You know, we're used to multiplying things together, typically makes them bigger than adding things together. There are a few exceptions, like if zeros involved and that sort of thing, but in general, sums are smaller than products. And König's theorem tells us that that general experience extends to infinite sums and infinite products. And this is one of the two major results today. König's theorem. I think it's probably the same König as in König's lemma that you did. König's lemma was in the exercise class yesterday. König's lemma is really a bit lemma-like. König's theorem is most definitely theorem-like. It's a very nice result. So we're going to have index sums of cardinalities. So if we have so we're indexing just by some arbitrary index set I here. And again, I'm going to use lambdas for cardinalities just because one doesn't have that many symbols around. So if these are families of cardinals, they don't need to be infinite. And what we're going to ask is that every kappa I is strictly below the corresponding lambda I. We're indexing by the same steps. So kappa I is strictly below lambda I for every index element, little I. And then what holds is the sum of the kappa i's is strictly less than the product of the lambda i's. Look, that's surprising because we're summing some things and then we're producting some larger things. Sums are typically smaller than products, so you would expect to get something like this. But one thing that's very nice about it is, I mean, it's true, it holds for infinite sums of products, and that's not going to be trivial. And the other thing that's unusual about this result is it establishes a strict cardinal equality. Sorry, not a strict equality, a strict inequality. You know, that's rare. None of the other results we're going to establish today establish a strict cardinal inequality. And we've only, I think on this course, we've only met one other result that establishes a strict cardinal inequality, which is yes.
Function. No, I forget what it's called, but the up to the aleph 0 is strictly less than f1. Or no, I thought it was consequence of repeatedly given the f of it.
Oh no, but I'm talking about cardinal. So cardinal, strict cardinal inequality, not to do rigidity theorems to do with ordinals. So I just mean Cantor's theorem that the cardinality of a power set is strictly greater than the cardinality of a set. And in fact, Cantor's theorem is a special case. So, corollary, we already had a proof of Cantor's theorem, but let's get it as a special case. Corollary, Cantor's theorem. I mean, it's Cantor's theorem. The Cantor's theorem we had worked in a choice-free world. This is Cantor's theorem in a choice world. But given that we've got the axiom of choice, Cantor's theorem is going to be a special case of this, because so Cantor's theorem says for any cardinality k, kappa is strictly less than 2 kappa. Okay, that's the cardinality of the power set. And how do we get this corollary from König's theorem? Well, we can say that kappa is equal to, just as we did before in the proof of the previous theorem, we can establish kappa is the same as the sum over all alpha less than kappa of the constant element 1. We're just summing together 1 alpha kappa many times. And by König's theorem, this is less than, well, 1 is less than 2, strictly less than 2, so this is the less, this has cardinality less than the product over kappa many copies of 2. So the product of kappa many copies of 2, that's the same as, it's like the way we went from an index, and you go from a sum of a constant thing is always just the constant thing times the index set of the sum, and a product of a constant thing is the set of function is the set of all functions from the index set into this. So this is the same. The set that we're counting here is the same as the set of functions from kappa into 2. So that's the same as 2 to the kappa. And here, this part here, the crucial inequality in the middle is König's theorem. Okay. So the main big task now is to prove this. So let's break it up into different tasks. So how do we prove a strict inequality? What's the general method? To prove inequality, we prove 2 non-strict inequalities. We prove that the left-hand side is less than equal to the right-hand side, and the right-hand side less than equal to the left-hand side. How do we prove a strict inequality? Typically.
So less than equal, and then find an element that's in the right hand side that's not.
Right. So first we prove it's less than equal, and then we prove it can't be equal. So that's a bit more. You prove it's less than equal by showing some injection from the left side to the right hand side, but it's not enough to find an element that's in the right hand side that's not in the image of the injection, because there might be some other bijection that you miss. So you need to prove there's no bijection or no surjection in that side to the right. But we'll deal with the less than or equals first. So to prove less than or equals, well, we need to give an injection from this set to this set. So what does this mean? So we define an injective function. So we defined the sum of the cardinalities to be the cardinality of the index sum of sets, where we were summing for every kappa I, the set of ordinals strictly less than kappa I. We want to find an injective function from that set into the product over the index set of the sets of ordinals strictly below lambda I. Okay. So we need to give such an injective function. Well, on the left-hand side, it's taking an element of the sum. So that takes an I and an alpha, which is something strictly below kappa I. And on the right-hand side, we need to map this to a function. That's going to, from the index set I, so it's going to take a new index element j, and we need to map this to an element of lambda sub I. Okay. Now, each kappa I is less than lambda I. So in the case that J is I, we can map to alpha. And in the case that J is not equal to I, well, what can we map to? Well, we need to find some element, some kind of canonical element of lambda J. But we can take such a thing because we know that kappa I is strictly below lambda. Well, kappa J is strictly below lambda J from here. Kappa J is strictly below lambda J. And so kappa J is itself an element of this set. So we can just map to kappa J. So if J is not equal to I. Let me check that that's the same as in the notes. Yes, it is. And then you check that this function is injective. And for you to understand what's going on, I suggest you check this for yourselves. I mean, I could explain now. It's very simple. It's just a case analysis. You assume you've got two non-equal things here, and they can be non-equal in two different ways. You can either have they're not the same because you've got two different first indices, or you've got the same first index and you've got two different ordinals. In both cases, you check that you map to distinct function. And it's very easy. Okay. So it's easily checked. At this inject. Okay. So I'm going to rub out the statement of the theorem, that we can remember what we're proving. So we now get to the tricky part, which is proving the drift inequality. We're going to prove that the two cardinals are not equal. So in other words, we want to prove there is no, in previous cases where we've been establishing strict inequalities, we've proved there's no surjection. But all we need to prove to show they're not equal is that there's no bijection. It's actually easier in this case to prove there's no bijection. So we prove there is no bijection from the sum of the capitalized to the product of the standardized. Sorry, well, we're talking about the sets here, so I'll make it the index sum of the sets ordinal strictly less than the capitalized, and the index sum of the sets of the ordinal strictly less. So we're going to assume we have a bijection and we'll get a contradiction. So what would be nice? It'd be nice to do this in a pictorial way so we can see what's going on. So we'll do that as far as we can. So the set of the capillaries, the sum over the capillaries, we can view, it's like a subset of the product, where the first element of the pairs is an index element, and the second element is the second element is taken from the set kappa I. And these kappa i's change depending on the index element. And we can kind of view it like this. So for each index element I, you'll have a set kappa I. So this is for the index I, and for another index j, you'll have a set of elements, say kappa j. Kappa j. And of course, we've got lots, potentially infinitely many index elements. But the sum as a whole is given by the set of pairs that consist of an index element together with an element of the set that it belongs to. So we can kind of view the sum as a whole as like a set that looks like this, where we've essentially divided it, we partitioned it into the different kappa i's and kappa j components, one for each index element. So what we're doing is suppose for contradiction. I'm just going to write hash for contradiction. That, or let's do it the way we do it. Linear. Suppose for contradiction that such a bijection exists. In that case, we have a bijection here between this sum set, which looks like this green box, to now, as far as I know, there's no good way of drawing a product set, but a large product. And if somebody has a nice idea how to do it, that's fine. But you know, since I don't have a nice way of doing it, we're going to do it like this. So we've got a bijection here. But the point is, this sum set we can view as this kind of partition index where each block is given an indexing element from I. And so each index element gives us like part of the partition of the sum set. So if we transport this via this bijection, we end up partitioning this function space into the image of each block. So we can write this set here as a disjoint union indexed by elements of sets that we'll call x sub I, where the point is x sub I is the image of this block for kappa sub I under this bijection, where that, so you know, this bijection maps this green block here to here, and kind of you get kappa sub I like landing in this set like that, and kappa sub j landing somewhere else. And these where these blocks land is partitioning this set, so we can write it as a disjoint union of the images of these sets. So xi is the image of the set indexed by I so of the block ki together with its index element, where this goes to under the bijection. Okay. Now, each of these blocks here, these xi blocks, it's like a set of functions from the dependent function space here, from this product space. You get a set of functions. And like in the proof of Cantor's theorem, we're going to do a sort of diagonalization. So each set of functions, each block has its own index element. We're going to look at those functions, and the way we're going to diagonalize is we're going to look at all the functions in xi and apply each of them at the index themselves at the index I. So doing this, we get for every index element I, the set which we're going to define as yi, which we'll define as if we consider, and maybe I should have used a symbol like f here, but we're looking at all the functions in the block x sub I, capital X sub I, and for each function we're applying it at index I. And because we're applying this x sub I, it's a subset of this product space. So when we apply it at I, we get an element of the set of ordinals less than lambda I. So this is a subset of lambda I. But this set, because it's so the set xi, should have mentioned this, each xi here is obtained by transforming the block of kappa sub I under this bijection and seeing where it lands here. And so each xi has cardinality kappa sub I, because we're simply transforming that block here under a bijection. So the cardinality of x sub I is kappa sub I. So yi is a set of cardinality kappa sub I, is a subset of lambda sub I of cardinality kappa sub I. But kappa sub I is strictly less than lambda sub I. So therefore, since the cardinality of, or rather, for the set of xi has cardinality kappa sub I, and for each element there, we've got a surjection. We have a surjection. So that function that takes an element of xi of the set capital Xi of functions to itself applied at the index I is a surjection from xi to yi. So we've got a surjection from the set xi of kappa sub of cardinality kappa sub I to the set yi. So yi has smaller or equal cardinality to xi. So the cardinality of y sub I is less than or equal to the cardinality of xi, which equals lambda I. Sorry, kappa sub I. So here we have a set of elements from a subset of elements of ordinals strictly less than lambda sub I, but that subset has strictly smaller cardinality than the whole set. Therefore, there's at least one, in fact, infinitely many elements of the set lambda sub I that's not contained in here. So therefore, but this is kappa sub I, which is less than lambda sub I. So therefore, the set lambda sub I take away yi is non-empty. And because it's a subset of ordinals, it has a least element. And now what we're going to do is we're going to consider a function that cannot land in the, we're going to find a function in here that cannot land in any, that we can prove does not belong to any of the xi's. So consider the function. We're going to map an index element little I to simply to the smallest ordinal in a set of ordinals strictly less than lambda I, with those in yi taken away. And it's easy to see that this is clearly in the product space, because we've defined it in that way. It's mapping every index element to an ordinal strictly less than lambda I. But it's also clearly not in any x sub I, because it differs at I from every element in x sub I by definition. But not in any x sub I. And that contradicts the fact that the function space was the disjoint union of all the xi's. That's a contradiction. Okay, that's a relatively tough proof. But and it would be, if anyone can think of a better picture than this. The notes don't have any picture, but anyway, this was the best I could do for the lecture. But in any case, it's a nice argument. If you didn't manage to follow it in the lecture, and I'm not surprised, but I think we should take some time to think about it, and also to compare it to the proof of Cantor's theorem, the original proof. And the kind of main similarity is the way that we're using. We've got our set of functions here, and then we apply them, each set xi, we apply the function at the index little I itself, and that's a form of diagonalization similar to what's being used in proof of Cantor's theorem. Right, okay, so having done that fairly heavy work, let's step back a bit and do some lighter things to do with product. So we now, König's theorems essentially our transition from sums to products. So let's now consider infinite products. As the main operation we haven't understood. Well, it's not true, it's the only operation that we haven't understood, because there's also cardinal exponentiation that we considered already back in the second lecture. We started looking at cardinal exponentiation. But now I want to just observe that cardinal exponentiation is actually a special case of product. So if we want to understand things, it will be enough to understand product. So the cardinal exponentiation is a special case of product. And actually, we've already used this. And I should have really done this before König's theorem, I think. So kappa to the lambda, the two cardinals, is just the same as, in the same way that the product of two cardinals was an index sum where the thing that you're summing is not dependent on the index. It's just the same here. It's the product function, the function space, or the exponentiation is again, because it's a set of functions, but it doesn't depend on the index here because you're always going into the same step. So it's just the product, the constant product here. So if we've understood product, then we understand exponentiation. And also exponentiation, we've looked at its laws in the past with respect to finite sum and finite product. It also enjoys laws with respect to infinite sum and infinite product. And indeed, one gets in cardinal arithmetic the laws that one would expect. So cardinal exponentiation enjoys expected laws. So if you take a product as a base and you take some power of it, then that's just the same as producting over all the powers. And the sums behave well, as you'd expect with respect to exponents. So if you take an exponential where you have kappa to the power of some sum, then that's the same as product. So the usual law that transports sums of exponents to product. Okay, so the many things behave in just the way we expect them to, but where the real tricky problem arises is the following. Well, what we would like, we know that all our cardinals are Alex, and we would really like some rule for computing exponentials in terms of Alex. So that leads to the question, challenge. We want to find a gamma, an ordinal in general, so that if we've got a cardinal exponential of infinite cardinals, we know how finite things behave, so let's look at cardinal exponential infinite cardinals. Actually, when I say we know how finite things behave, we know how exponentiation behaves when both numbers are finite. So actually, there are other cases of this where one is finite and the other is not, and they are also of interest, as we shall see. But anyway, this would be a very general question. Given alpha and beta, can we find a gamma such that, yeah, we understand cardinal exponentiation because we know when we've got an exponential here, we know where it lies in our numbering system of cardinals. Can we find that? And this question is not easy to answer. In fact, arguably, it has no good answer. Arguably, no good. What we're going to do in the third part today is we're going to look at the little that we can say about this question, and it really is very little. Maybe just before the break, just to say there is one answer that answers everything. There's the so-called generalized continuum hypothesis. Also called GCH. So can anyone in this room state the generalized continuum hypothesis? we've done it, we've met it on the course already, but can we move this data off your head?
The alpha, the alpha.
Very good. For any cardinal alpha, aleph alpha, 2 to the aleph alpha, the power set, so any infinite power set is always the smallest cardinal it could possibly be. It needs to be strictly greater than aleph alpha, but it's just the next cardinal up from aleph alpha. So that's aleph alpha plus 1. Very good. That's the generalized continuum hypothesis. And if one has this, then all questions, it doesn't, here we've only got 2 in the base, but anyway, all questions about cardinal arithmetic can be answered. Okay? But, why you would want to assume this is an axiom? If it were true, one might want to prove it, but actually it can be proved that it can't be proved from the axioms, and it's also its negation can't be proved from the axioms. So it's independent of the axioms. There's no good reason to assume it's true. It's very hard to understand what this is really saying and why it should be true. But it's one of the benefits of having it is we would be able to answer all questions about cardinal arithmetic. But we're not going to assume generalized continuum hypothesis. So in the third hour, I'm going to look at what we can say, which is very little, about the cardinal arithmetic of exponentiation. Yes, Vasily?
Why would anyone assume that? Yeah, what people would this is true?
Yeah, there are essentially 2 reasons that people do sometimes in very unapplied mathematics consider this axiom. One is there's a natural model of this axiom called the constructible universe, which is due to Gödel. And some mathematicians like that universe. It's all sets are very sort of tame in some sense in that universe. Some mathematicians like it, and then you say, assume the axiom, we live in the constructible universe, otherwise known as V equals L, and then this is the theorem, the generalized continuum hypothesis. And as I say, some people like to believe that we live in that universe. Very few. There are some. Another reason that people assume it is because you can get some mathematical consequences from it sometimes. So for some mathematical theorems become easier to prove, or in the case that you have this axiom. Sometimes some results, mathematical results, have actually been proved, assuming the continuum hypothesis is true, and you prove it, and you assume it's false, and you also prove it, and then you can see that it's true. I'm not sure if one ever involves the generalized continuum. Anyway, good question. Break time. It's quite past, but still, let's start again at 1:15 to finish earlier. Okay, so we don't have the generalized continuum hypothesis in general, unless we assume it. We see no good reason to assume it, apart from that it would simplify cardinal arithmetic, but we will be talking about the true universe of mathematics. If we did so, who knows? Are we anyway talking about the true universe of mathematics? No, it's that. But, anyway, so what can we prove? So I'm going to tell you 3 things we can prove, and actually, rather than looking at generalized products, I'm just going to focus on exponentiation, simple case. And rather than looking at general exponentiation, I'm just going to look at 2 to the power of an exponent, because that's already, that case basically has the main complexity in it. So we're basically looking at cardinalities of power set, because 2 to the power cardinal is the cardinality of the power set of cardinal. So there are 3 main things we can prove about 2 to the aleph alpha. The first one, I'm going to call them A, B, and C. The first one that we can prove is that 2 to the aleph alpha, we can't prove it's equal to aleph alpha plus 1, we can prove it's greater than equal to aleph alpha plus 1. Well, of course, that's obvious. 2 to the aleph alpha is a strictly greater cardinality than 2 to the aleph alpha, than aleph alpha itself. And aleph alpha plus 1 is the next greatest cardinality after aleph alpha, so this is obvious, except it does rely on the axiom of choice, that we know that the cardinalities are lying in a linear order. Without the axiom of choice, this is not true. Second thing we can prove is that if alpha is less than or equal to beta, these are ordinals, then the power set of aleph alpha is less than or equal to the power set of aleph beta. Well, we already know this. We know that power set preserves cardinalities. We saw this in the second lecture, 2 to the. So here, we know that aleph alpha is smaller than or equal to aleph beta, and we know that 2 to the power of preserves the order of cardinalities. So we already know this. It's not new to us. So what is used is going to be property C, which is what we're going to spend the rest of the lecture on. And this is another relatively deep result about cardinal arithmetic. There are basically 2 deep results today: König's theorem and this. And this theorem says, this is a theorem. So for every alpha, we don't know what 2 to the aleph alpha is, but we do know a property that it needs to satisfy, which is that something called its cofinality has to be strictly greater than aleph alpha. So CF of kappa is called, and I haven't defined it yet.
So number 2B, A, B, C, because we have A, 2, C, right? Not the
Sorry?
back on the previous slide.
Yeah, sorry, this is B. Yeah. So this is called the cofinality of kappa. What does this mean? Well, let me make the definition. And I'm going to define the cofinality of any limit. So if alpha is a limit ordinal, then its cofinality which is CF of alpha is the smallest ordinal gamma, okay, such that alpha is the limit of an increasing sequence of ordinals of length gamma. Well, what's an increasing sequence of ordinals of length gamma and its limit? Well, we actually did sequences. We did ordinal length sequences already last week when we did transfinite dependent choice. But just to remind you and to get the terminology right, so an increasing increasing sequence of ordinals of length gamma is a sequence, an ordinal index sequence. So that's, I mean, I'm defining what increasing sequence of ordinals of length gamma, let's underline the whole thing. So it's a collection of ordinals indexed by ordinals less than gamma. So that's a sequence of things of length gamma, that's what that means. And the increasing property, so this is sequence of length gamma, and the increasing property in this case we said increasing means strictly increasing. So satisfying beta less than beta prime implies alpha beta. So if beta is strictly less than beta prime, then alpha beta is strictly less than alpha beta prime. So normally one would say strictly increasing, but whenever we talk about increasing sequences of ordinals, we're going to mean strictly increasing. So we're just going to save ourselves the word strictly by not mentioning to it. And then the limit of such a sequence, the limit of such a sequence is just the supremum. So we could just say the supremum, but it's traditional to talk about, when you have an increasing sequence of ordinals, to talk about the limit of the sequence. But it's just the same thing as the supremum. So we write it like this: the limit as beta tends to gamma of alpha sub beta, and that's just defined to be the supremum over the beta less than gamma of alpha. With that definition to hand, might seem quite a lot to swallow, but it should be easier when we look at some examples, which we're now going to do. So let's look at the cofinality of some ordinals. So the ordinal omega, we want to look at the cofinality of the ordinal omega. Well, omega is the limit, or the supremum, of the sequence of finite ordinals. That's an increasing sequence. It's going strictly up. What length is it as a sequence? Sorry? Yeah, it's length omega. So this is a sequence of length omega. Can we get by with a shorter increasing sequence of oh, sorry, gamma is assumed to be a limit ordinal here. So we can't get by with a shorter sequence because the only limit ordinal we could use would be 0, and we wouldn't have anything to approximate omega with. No, we can't. So this is the shortest length of sequence of smaller ordinals that gets us to omega is length omega, but the cofinality of omega is omega. Okay. What about the cofinality of, what do I have in the notes? Yeah, what about the cofinality of, say, omega squared? Well, omega squared, we could get it as, again, a sequence of all ordinals below it, which would be of omega squared. But we have a shorter sequence this time, because it's the limit of the sequence omega times 2, omega times 3, omega times 4, and so on. The limit of that is omega squared. With the cofinality, again, we can't have a sequence shorter than omega, so the cofinality of omega squared is omega. Okay, let's go up. Let's take a big jump and go up to omega 1. So the cofinality of omega 1 is, well, now omega 1 is the limit over all ordinals less than omega 1, we write it like this. Alpha tends to omega 1 because we're thinking this is an increasing ordinal sequence. I mean, it's the limit of all ordinals strictly below it. Every limit ordinal is the limit of the ordinal strictly below it. But can we get by with a shorter sequence than omega 1? Well, any smaller sequence would be a countable ordinal. And if you have a countable ordinal, then your supremum is going to be a countable union of countable sets, which is going to be countable. So it's not going to take us into the uncountable. And omega 1 is the first uncountable ordinal. So we can't do better. So the cofinality of omega 1 is omega 1. And similarly, the cofinality of omega 2 is omega 2. So remember, these are the initial ordinals corresponding to aleph 1 and aleph 2. And you go on like that. But an interesting case holds when we get to the cofinality of omega sub omega. Because omega sub omega is the limit of omega, omega 1, omega 2, omega 3, omega 4. So although it's a larger cardinal, we can actually get to it with only an omega chain of approximations of smaller ordinals, which in this case are cardinal. So the cofinality of omega sub omega goes down to omega. Now, one thing you might notice is the cofinality on the right is always, all the ones we've seen, they've all been initial ordinals. And this is a theorem. We'll call it a fact. We're going to prove this 2 weeks from now. We don't need it today, so fact, the cofinality. So CF alpha is always an infinite limit, an infinite initial order. i.e. an alpha. So actually, when one's talking about cofinality, one often talks about the cardinality rather than it's defined as an ordinal, but in the end you get an initial ordinal, so you get a cardinality. So one often talks about the cardinality. So we might say the cofinality of omega is aleph 0. The cofinality of omega squared is again aleph 0. Cofinality of omega 1 is aleph 1. Cofinality of omega 2 is aleph 2. Cofinality of omega omega is aleph back to aleph 0. And also, although we're talking about cofinalities of ordinals and it's defined in that way, we're going to be particularly interested in the cofinalities of cardinals. So, of course, the cofinality of the cardinal means the cofinality of its initial ordinal. And here we're showing the cofinality of aleph 0 is aleph 0. The cofinality of aleph 1 is aleph 1. The cofinality of aleph 2 is aleph 2. And the cofinality of aleph omega is aleph 0. Okay. So what does this theorem tell us? So here we're talking about cofinalities of cardinals. I said the cofinality always gives us a cardinal, and by the cofinality of the cardinal, we mean the cofinality of the corresponding initial ordinal. So what information can we get from this theorem? And we actually get something interesting here. For example, about the cardinality of the continuum. So this is related to Cantor's question, his continuum hypothesis. We're trying to pin down the cardinal of the continuum. The continuum hypothesis is very rigid. It says that should be aleph 1. We're not, we don't see reasons to assume that, but what can we actually prove about the cardinality of the continuum? So the continuum is 2 to the aleph 0. So the cardinality of 2 to the aleph 0, well, we know it's not equal to aleph 0, obviously, because it's greater than or equal to aleph 1. So it is possible that it's aleph 1, but it need not be. It might be aleph 2. It's also possible. And there's quite a group of set theorists that believes that the cardinality of the continuum really is aleph 2, as a matter of fact. But it might not be. According to our axiom, it's consistent for it to be aleph 3. That's also possible. And we can carry on. But can it be aleph omega? It can't be aleph omega because the cofinality of aleph omega is aleph 0. And the cofinality of 2 to the aleph 0 is required by this theorem to be strictly greater than aleph 0. So this rules out, and this one is ruled out by the above, by the theorem. Similarly, it can't be aleph omega times 2, it can't be aleph omega squared. Yeah, sorry, Yuri.
We have only finite.
Oh, sorry, Russell. Sorry?
We have only finitely many plus.
Look, so there are infinitely many here. Aleph 3, aleph 4, aleph 5, aleph 6, aleph 7.
No, countably infinite number.
Well, actually, no, because it's possible for it to be aleph omega plus 1. This is possible. And in fact, it can be arbitrarily large. It can be an arbitrarily high ordinal, just not any. It just can't be aleph alpha of an alpha that is that has cofinality aleph 0. And there are lots of alephs that have lots of cardinals that have cardinality, but cofinality aleph 0, but many more than that. Anyway, so it's a curious thing. You can rule out some cases, but yeah, basically, it's been proven that the cardinality of the continuum can be aleph anything as long as the anything doesn't have cofinality aleph 0. So this theorem is the only obstruction. Right, so I want to prove the theorem. And the theorem involves a technical lemma and then a nice proof. So I shall state the technical lemma and do the nice proof, and then we'll decide how much time and energy we've got, and whether we want to see the technical lemma proved or not. By the way, my take on this is, you're trying to answer a question whereabouts the continuum lies in this hierarchy of well-orderable of alephs, which are like the well-orderable cardinalities. But you kind of one way of looking at it is you've forced the problem on yourself by assuming the axiom of choice that tells you that the continuum is well-ordered. Because it's well-orderable, but you have absolutely no control over what the well-order is like, more or less. And that's why it could kind of land here. So, an alternative view is just that maybe the continuum shouldn't be well-orderable, and we shouldn't even be trying to fit it into this picture here. But anyway, today we've assumed the axiom of choice. So So it is well alterable. It needs to fit somewhere. It's certainly aleph something, aleph alpha for some alpha. And all we can prove about the alpha is that it's greater than or equal to 1, and it doesn't have cofinality of 0. Right, so we're going to prove the theorem, and the technical lemma is this, that this again uses the axiom of choice. Every infinite cardinal, well, basically everything can be of choice, but every infinite cardinal kappa, or probably not everything, but lots is using the axiom of choice, can be expressed as a sum of smaller kappas There's a mistake in the notes here. I shall correct that. So can be expressed as the sum over where so every cardinal can be expressed as a limit of smaller cardinals of its cofinality, but not just so that we have from the definition of cofinality, but actually what's useful is that we can get it as a sum of smaller cardinals. The cardinality is a sum of smaller cardinals of smaller cardinality. The sum of its cofinality many cardinals of smaller cardinality. Right, so that lemma is, as I say, technical. And using the lemma, we're going to prove the theorem. So the proof of the theorem, we need to show this inequality. And this proof is actually relatively short and neat. So we need to show by the way, I said König's theorem is unusual in establishing a cardinal inequality. In a sense, this is also a strict cardinal. In a sense, this is also establishing a strict cardinal inequality. It's more a property of the cardinality that the exponential has. The power set. So we need to show this. So by the lemma, just the line above, we can express 2 to the alpha, 2 to the aleph alpha is equal to the sum of let's put beta because I've got beta in the notes. A sum of kappa sub betas of length of cofinality of 2 to the aleph alpha many kappa sub betas, where each kappa beta, every kappa beta is strictly less than 2 to the aleph 0, 2 to the aleph alpha. So by König's theorem, earlier, one relating sums and products, we're not using König's theorem for this first inequality, right? First equality. So we have 2 to the aleph alpha equals the sum from the lemma over the cofinality. So this sum, 2 to the aleph alpha. Oh, hard to draw a small aleph. maybe because they're such large things. So if you've got the sum of the kappa betas, so each of these kappa betas is strictly smaller than kappa. So by König's theorem, that's strictly smaller than the product over the betas less than the cofinality of 2 to the minus alpha of kappa. And this equals, each kappa beta is less than 2 to the alpha, so this equals 2 to the aleph alpha. And this, because it's a product of things that don't depend on the index, this is simply 2 to the aleph alpha to the cofinality of 2 to the aleph alpha. Okay, so now we want to suppose the contradiction. We want to prove this strict inequality. So let's suppose the contradiction that it's false. So suppose for contradiction that this is false. So in other words, that aleph alpha is less than, sorry, that then the cofinality of 2 to the aleph alpha is less than or equal to aleph alpha. But if we do that, well, the cofinality of 2 to the aleph alpha is then, this then allows us to carry on this reasoning here. If this is less than or equal to 2 to the aleph alpha to the power of aleph alpha, but by exponential arithmetic, this is 2 to the aleph alpha times aleph alpha. And using our old friend that every cardinality is its own square, infinite cardinality, this is 2 to the aleph alpha. Hang on. Oh, yeah. And what we proved is that 2 to the aleph alpha is strictly less than 2 to the aleph alpha. And that's a contradiction because obviously it can't be strictly less than itself. That's, well, this is a contradiction. Right. So that's the main content today. There is still the proof of the technical lemma. We've got, I want to finish at 5:02, but we've got 10 minutes, so let's do it. And yes, it's in the notes. But anyway, let's actually, we're not covering all the technical things all the time, so let's do this one. So we just want to prove the lemma. This is the sort of technical thing that I leave my notes. Right. So we've got an infinite cardinal kappa. We want to prove that it can be expressed as the sum. So by definition of cofinality, by short the definition of CF for cofinality, we have that kappa is the limit of some increasing sequence of length its cofinality of, and I'm going to use beta sub alpha, where beta alpha and increasing sequences. an increasing sequence. Because the cofinality is the shortest sequence that we can get kappa in this way from, so we can in particular get kappa in this way. So the point is, we're getting kappa as the limit of this increasing sequence of beta alphas. So we've like got beta 0, beta 1, beta 2, beta omega, say beta omega plus 1, beta alpha in general, and all up to all these, the sequences of length cofinality of kappa. We have the limit alpha tends to cofinality of kappa of beta alpha is kappa. And if we look at all the ordinals less than kappa, you know, we've got like all the ordinals up to beta 0 here, all the ordinals between beta and beta 1, beta 0 and beta 1 here, all the ordinals between beta 1 and beta 2 here, and so on. So we can partition kappa. We can write kappa as the disjoint union over alpha strictly less than the cofinality of kappa of the set of ordinals strictly below alpha with the set of ordinals with the union over all alpha prime less than alpha of the sets of ordinals strictly below beta alpha prime removed. But the point is, this set of ordinals is something like this. Here we have the limit of all the ordinals to which we get to from alpha prime strictly below alpha. And then we've got all the ordinals between that and beta sub alpha. Okay, so here this would be the case for 0. We have this block. The case for 1, we would have this block. The case for 2, we would have this block, and so on. Okay, and we're partitioning the ordinals into that way. And I'm going to just use notation for this. So I'm going to write this the disjoint union over the alphas of, I'm going to write B sub alpha. So this is B0. I hope the B's look a bit close to the betas, which is why I chose the B. But we need to distinguish them on the board to make sure. So anyway, beta alpha is a particular ordinal, and B sub alpha is a set of ordinals strictly below beta alpha, and it's the block immediately below beta sub alpha. So this is B1, B2. Okay. So each B sub alpha each B alpha is a subset of, it's a set of ordinals strictly lower than alpha. And since every beta alpha is strictly below kappa, and kappa is an initial ordinal, because it's a cardinal, we have that the cardinality of that set, sorry, but this is beta sub alpha. I really shouldn't have used B and beta. So we have the cardinality of the set B sub alpha is less than or equal to the cardinality of beta sub alpha. And because kappa is an initial ordinal, that's strictly less than kappa. Okay. And since this is a disjoint union, we have that the cardinality of this disjoint union is the same as the cardinality of the sum of cardinalities. Because sums are just like disjoint unions with a labeling attached. So we're nearly there. Let's see if I can fit it in here. So the ordinals below kappa, so this is the ordinals below kappa, is the well, I've already written this here. So this equals kappa because that's the same as kappa here. So kappa is the sum of yeah. It's the cardinality of these sets, and each B alpha, each cardinality B alpha is less than kappa. So indeed we've got it as the sum of strictly smaller cardinalities there. So we're done. And there's an exercise in the notes, which is just to verify that when you have a disjoint union of sets, the cardinality of the disjoint union is the same as the cardinality of the sum. But it's kind of obvious as well. Yes, that's a
So what is there verified? You know, if one.
well, the underlying sets are different. This is a disjoint union.
Right.
So it's just a union of some sets. And here the sets are just pairs. It's a subset of a product.
Oh.
So it's a trivial thing at this stage in the course. Right, any other questions? Okay, so as I say, today's material, and it's more the calculational side involving like manipulations of being able to calculate things with cardinals that will be that may be in the quiz in 2 weeks' time. Next week's lecture is going to be a sort of slightly out of the main thread of the course on applications of the axiom of choice, because there's not going to be an exercise class related to that, but there'll still be some orally examinable material in next week's lecture. Okay, any other questions? Right, so wish you a nice week and see you next week.